All right, this is Workplace 30, Chapter 2 review. We'll just go over some of the important things in Chapter 2. The first thing I want to start off with is metric conversions. Okay, we talked about the metric staircase, and being able to convert from one unit to another is pretty important. So if you have let's say 3 kilometers and you're asked to express that in meters, you need to know what that ratio is. So instead of memorizing this times 1,000 or this divided by 100 or whatever to get from one to the other, it's the most common, I think for me, the best way for me to learn and to remember is to use the metric staircase. So I think this is what I've taught you in the lessons. So as we review the metric staircase, I usually put the base unit. So if we're talking about meters in this question, the meters would be the base unit here. But we could talk about seconds or whatever it is, right? So when you go down the staircase, that's a factor of 1/10, okay? So it's 10 times as small. It's 1/10. So this would be decimeters, and then another 10th would be centimeters, and another 10th after that would be millimeters. And so your base unit, if you go down the steps, the easy thing to remember is to move the decimal place to the right. If you go up the steps, then you move the decimal place to the left. Each factor of 10 is 1 decimal place. So 180 centimeters is how many meters? Well, let's just take a look at what you do here is you start at the unit that you're given, and then you work the steps until you get to the unit you want to go to. So centimeters is here, and I would go 1, 2 to get to meters. And if I go 2 to the left, that means the decimal place, which is understood to be right at the end of this number, goes 1, 2 to the left. So this is 1.8 meters. Okay, and you can put the 0 there if you really want. I'm not too worried about that. All right. So again, if we want to do millimeters to meters, you start at millimeters here, and you go 1, 2, 3 steps to the left, and so the decimal place goes 1, 2, 3 to the left, and that's 76 meters. So 76 meters is 76,000 millimeters. All right. Okay, and as we move through here, meters now to kilometers, so we're going backwards again, 1, 2, 3. So 1, 2, 3, 8.4. Decimeters to millimeters. Here's one where we go to the right. 1, 2 steps to the right. So if we have to move our decimal place beyond the numbers that are given, we just always add zeros, right? So in this case, if I go 1, and now I got to go another one, so I add another 0 there. So 9680 is your number. Okay? And yeah, if we were going, let's do an E here. If we had 35 centimeters equals how many kilometers? Well, then you would have to start here at centimeters and go 1, 2, 3, 4, 5 spaces to the left. And in this way, we go 1, 2, and then when there's no more numbers, we add zeros. So 3, 4, 5, and then you put your decimal place right there. So this is 0, decimal, how many zeros? 1, 2, 3. 2, 3, 3, 5. Okay, so it's that many kilometers. Okay, so again from here we go 1, 2, 3, 4, 5 to the left. You move the decimal place 1, 2, 3, 4, 5 to the left. Any questions about that? Anybody online have any questions about that? Virtual learners or in the classroom here? No? Okay, we can come back if you need to later. I do want to talk about this as well, though. Rounding measurements. I find that this is still a little bit difficult when you don't review. So when you round a number, that means you're shortening it, and the last digit is where you round it to. So if we're rounding the measurement to the nearest tenth of a unit, the tenths is the first decimal place. Okay, that's the tenths. So what you want to do is you want to focus on this number right here, the tenth digit. And then you always look to the right, okay, the number to the right of it. If it's 5 or greater, this number to the right of it, you would round the 10th unit up. If it's 4 or less, so under 5, then you keep it the same. So this one is actually, when we round it, it's 567.3 millimeters, right? Because 7 is greater than 5, so this goes up to the next one, goes up to 3. That's what it's closest to. That's really what you're asking. All right, over here, the nearest tenth, well, this 0 right here is the tenth for D, and so I look to the number to the right of it. It's a 5, so this would go up. So if I were to round that, it would be 0.1 kilometers. Hundredth is the second decimal place. This one would be 92.79 because there's a 6 to the right of it. Okay, what about D over here? So 640.4, what do I write? 6.0.4. Do I leave it as a 1 or do I write it as a 2? 1 or 2? Sorry? So the nearest hundredth, let me help you. The nearest hundredth, this is the hundredth spot, the 1. So I look to the number to the right of it. If it's greater than 5 or greater, then we bump it up. So yeah, it's 2. Okay? The nearest whole unit, well, this would be the whole unit here. That's whole. So that's just the whole unit. So 2,987.786, while we want to take a look at this number and then the number to the right of it. So that's 2988 kilometers. This one over here, the nearest whole number right here, we look to the number to the right of it, it's 0. Because this is less than 5, and so 0 stays as 0. Got it? Good? Okay, you're speaking for the whole class pretty much here right now.
When we're writing a test,
yeah.
What?
All right, so the question was how many decimal places do you usually round to if the question doesn't state? And I just generally say 2 decimal places is fine. You know, if you're talking about very small measurements like 0.00000357, then you don't want to go to 2, you want to go to 7 or whatever your question is using there. But for now, just 2 decimal places for regular stuff is good. Okay, so here's another type of question. This is not rounding, this is not metric conversions. This is talking about precision, okay? So precision, we also talked about accuracy. Now let me get to the workbook here if I can find out, there we go. So precision and accuracy is something that we studied, and accuracy is how close a measurement is to the actual true value, all right? So if you said water boils at 60 degrees Celsius, that would not be a very accurate statement because water boils at 100. So that's not real close. Now, how close is accurate? Well, that's up for debate. Obviously, 99.7 degrees Celsius would be much more accurate than 60. We do know that. The other thing that we need to talk about is precision, and that's what we talk most about here is precision and uncertainty. So precision is related to exactness. So recall, precision is sort of how, oh boy, got computer problems again. Precision is related to exactness, so it's basically how precise can you be, right? And so it is also related to the units of measurement on the measuring device. So you've learned this in your lessons, but as we just review here, Canadian swimmer Anna Mae Pierce recorded a time of 2 minutes 20.12 seconds, looks like. Yeah, minutes, seconds. So 2 minutes, 20 seconds, and then 0.12, 12/100ths of a second in the 200-meter breaststroke. What is the precision of this measurement? If you're asked for a question like this, and it doesn't tell you, it doesn't show you a ruler, or it doesn't show you the stopwatch, you're just given numbers. What you do is you look at the very last number, and whatever place that's in, that's your precision. So for example, this is measured to 2/100ths of a second, right? So it's 12 100ths, or there's a 2 in this hundredths spot. So the precision would be, this would be, the measurement tool appears to be exact to the nearest 100th, because this number could be 2 or 3 or 4 or 7 or whatever. So this is the hundredths of a second, so that's your precision, okay? You look at the measurement tool. If I said 56.7 centimeters, what's my precision level? Well, you would say 0.1 centimeters because that's the last digit that you see. All right, that's another example. So what's the precision? Now, what is the range of possible values for her actual time? Okay, so the range of possible values, this covers a couple different concepts. It talks about uncertainty. So if I go back to the workbook here, it talks about uncertainty, which is sort of the margin of error of the measurement. So if you have a certain precision, you also have a certain uncertainty, and that uncertainty is really half of the precision, okay? the uncertainty would be half of the precision. What do I mean by that? Well, if you have this as your measurement up here, and you have this as your precision, that means that this time could possibly have been 2 minutes 20.12 seconds plus or minus, now this is where the uncertainty comes in, half of this precision number. So 0.01 divided by 2, which is 0.005, I guess. You see that? So the uncertainty is half of the precision. It could be above or below. So what's the range, the possible range? Well, you'd actually have to just state these two numbers. So if we subtracted 0.005 from here, what would that be? It's 20.07. Looks like. No, that doesn't seem right. Give me a second here. 0.115. Okay, so we got our calculator out here now. We're going, so 0.12 minus 0.005. Oh, I'm frozen. Technology is awesome sometimes. What'd you get there in your calculation? 0.115. Thank you. Okay, 0.115. That is correct. So this would be like 120, so we'll take away 5, what is that, tenths, hundredths, thousandths, take away 5 thousandths, and that's 115 thousandths then. Thank you. So that's the minimum. That's the minimum value. So the maximum value would be 2.20.120 plus 0.005, right? Which would be a little bit easier to calculate. 20.125. Okay. So there you go. That's the range from here to here. The minimum that it could be to the maximum, considering the uncertainty. All right. We got through that. Awesome. Okay, so that's 2.1. Any questions about 2.1? All right, we'll move on to 2.2. They asked you to review sort of adding and subtracting fractions. Now, are you able to use your calculator? I have no problem with you using your calculator to add fractions, but just in case you have to add fractions, you know, manually, you should know how to do this. So when you add or subtract fractions, first of all, they have to be in improper fractions or fractions, not mixed fractions, so proper or improper. You want to convert this one. So let's actually start with B. So how do you convert this to an improper fraction? If it's a mixed fraction, you go 4 times 2 plus 1. So what's that? 9 over 4, and you put this on the bottom again. Okay. So now you get to this point, you have to have a common denominator. Okay. So that means I have to express one or both of these in a different denominator so that they're the same. So I'm going to multiply by 4, top and bottom here. So that's going to be 4 over 8 plus 1 over 8, and that's going to be 5 over 8. Then when you do that, you add the top, and then you just keep the bottom. So you have 4 eighths, plus you add another 1 eighth, you get 5 eighths in total. And this one here, so I'm going to multiply by 4 here, times 4 times 4, that's going to be 36 over 16, plus 1 over 16, that's 37 over 16. Okay? So if you have to add or subtract fractions, common denominator. All right. We start getting into talking about something called nominal value. Okay, the nominal value. The nominal value, when you're given a range of measurements, the nominal value would be the average of those two. Okay, so you might remember that from your studies there. The nominal value for these measurements, sewing a pair of pants. Okay, anywhere from 33 3/4 inches to 34 1/4 inches. The nominal value, and I've got the answer key kind of over here, if you want to take a look here while we do that, is basically the average. Okay, so you add the two and divide by 2. So what's the number that's right in the middle of those two measurements? So you add the two, and we have a nominal value of 34 inches. So you can see that this number is 1/4 of an inch under 34. This is 1/4 of an inch above 34. So our nominal value is 34. Now the tolerance, okay, so the tolerance is sort of like the uncertainty here, really. Okay, so the difference here between the two measurements is 1/2 of an inch. It's 1/4 and 1/4. So the nominal value plus or minus the range would be the average plus or minus half of the range. Okay. Okay, so then here we go. The tolerance is 1/2 an inch, so you can tolerate a difference in total of 1/2 an inch. And the plus or minus the range is kind of like the uncertainty. So 34 inches plus or minus 1/4 inch. So I need you to see how the range from this measurement to this measurement can be expressed the same way this way. The average plus or minus half of the total range. Okay. Now, what is the tolerance? So the tolerance would be kind of like the uncertainty. Okay, tolerance is very similar to the uncertainty in a measurement, although it's related, but they're not the same. The tolerance would be, okay, how small could this possibly be up to how big could it possibly be? What's the tolerance there? So the tolerance is the difference between the smallest and the largest, which is 1/2 an inch. And then this last part here, write the dimensions in this form. Okay, this is strange. You don't do this every day. But what you do is you can write it as the minimum value, so the smallest possible value, plus the allowable tolerance greater than, or you could say the maximum value minus the maximum tolerance the other way. So we would write minimum value, which was 33 3/4 inches. And then we would write the tolerance would be plus 1/2 an inch and minus 0, because we can't go any smaller. That's one way. That's the way to write it, like this. The smallest, and then you can go up 1/2 an inch. Or you could write the largest measurement possible, and then you go plus 0, can't go any higher, but you could go down 1/2 an inch. And that's what's stated over here. So that, I know that's a little bit strange there. It's a lot of little notation. But you probably are going to be asked to do that on your test. So just make sure you have all those things straightened out. So the nominal value is like the average. The tolerance is like the uncertainty, or the range. And then this way of writing it. Okay, any questions about that? Okay. All right, a little bit more practice here. What's the maximum and minimum values represented by each of the following dimensions? Okay, so here's a little practice with that. If you have 350 Fahrenheit plus or minus 5 degrees Fahrenheit, what are the maximum and minimum values? Well, pretty easy. A minimum would be 350 minus 5, or 345 degrees Fahrenheit. And the maximum would be 350 plus 5. And that would be 355 degrees Fahrenheit. All right. Working with the inches and working with fractions, you may or may not know how to do this, right? But again, if you look at this like a regular subtraction and you get a common denominator, okay, so this is now 18 over 1. You could write them both over 8 and do it that way. Or if you remember your tape measure. So I have a tape measure here, and this one has measurements in inches and centimeters, which I like, but you can see what 18 inches, so I'm looking at 18 there, minus 1/8 of an inch, right, would be going back to, and you can't really see this for those of you at home, but if you subtract 1/8 of an inch, that is actually 17 7/8 of an inch, because if 1 inch is divided into 8s, you go back 1/8, you would have 8 over 8 minus 1 would be 7 over 8, and then all the way to 18 1/8. Okay, so you could do it this way and come up with an answer using common denominator times 8 times 8, or you could think about your tape measure. Okay. All right, maximum minimum value. Well, what does this look like? This looks like a maximum value, because you can't add any more here. It's adding 0, but you can subtract a whole 0.5 millimeters. So it looks like the minimum is what? 24.5 millimeters. That's the minimum value. And the maximum value is this given 25 millimeters. Okay, remember that's just that notation that we just learned. Okay, so here are the, let's see, okay, yeah, those are those solutions for A, B, and C. If you want to try D, E, and F, you can. I just wanted to kind of give you a brief introduction there to that type of question. So any questions about that at all? And again, I would change mixed fractions into improper fractions and then do your addition. Okay. All right, moving on here. We're almost done. I think this is the last question that I had planned for this part of the review. But an electrical resistor has resistance with a nominal value of 100 ohms and a tolerance of 3%. Now, when we talk about tolerances in terms of 3%, that shouldn't be too scary for you. Basically, all that is the acceptable range or the change would be 3% of your initial value. Okay, so what's the range? Well, we have 100 ohms. We know that that's our average. That's our nominal value. So we could go up a certain ways from that and down a certain ways from that. If the tolerance is 3%, that means that we have 100 ohms. We can go plus 1.5%, or we can subtract 1.5%, if that makes sense. Okay, so we can go 1.5% above or 1.5% below. So 3% of 100, well, that's 0.03 times 100, of course, is 3. So that turns out to be 3 ohms there. So we could go from 90, so we get minus 1.5 ohms. So that's 90, what's that, 98.5 ohms, all the way up to 100 plus 1.5 would be 101.5. Okay, so if the tolerance is in percentage, just turn that into an actual value with units, and then you can add or subtract. B says, write the resistance in the form of the nominal value plus or minus a half of the tolerance. Okay, so that's also the same as half the range. So we would have 100 plus or minus 1.5 ohms. Right? So half of the tolerance. 100 plus plus or minus 1.5 ohms. All right, I'm gonna pause here right now, and then I'm going to ask you to come up with some specific questions. If there's any other questions that I didn't cover, types of questions I didn't cover that you would like to see, I'll let you figure that out, okay? All right, workplace 30. So if there are no other questions here, just a reminder what we are talking about. We're talking about, in chapter 2, talking about metric conversions, talking about rounding, we're talking about accuracy, precision, we're talking about range of values, we're talking about uncertainty. We're also talking about nominal value and tolerance, which is sort of like the average value and the uncertainty in a sense. Okay, different ways of expressing the range of values, and some questions regarding that sort of thing. So that's your general review for chapter 2.